Good morning. My name's Mr. Cosmo DiLiegro. I'm here at Harry S. Truman High School, and we're going over beam analysis. I'm hoping that by this point in time, you have already completed the notes and you understand what the different delineations are as far as structural members, such as joists, stringers, floor beams, or girders. We discussed when we were looking at loads that when a load is applied, such as a floor load or roof load, you see how that load is applied downward, and then that load is distributed amongst the beams. Remember when we looked at tributary area, you notice how the beams take up that load. Now, the beams transfer that load to the girders, which in turn transfer the load to the columns, down to the footing, down to the foundation, down into the soil, which is why soils and foundation design are very important. We will look at that subsequently. Okay, so very important, static equilibrium. We discussed this ad nauseum in POE when we looked at truss analysis. Beam must be in static equilibrium to successfully carry loads. So here we have a beam with an applied load a certain distance away. Note that forces are often referred to as vectors. And so we have our applied load and we have our two reaction forces at the ends. A reaction force is often called a shear reaction, and a rotational reaction is called a moment reaction. So here they use F or R to delineate the reaction forces, and I fluctuate between the two. Here we have our different supports, beam supports. Okay, that first one is called a roller or a rocker support. You'll see this on bridges where one end of the bridge you're going to have a rocker connection and the other end will be a fixed pin connection. Okay, and I can show you differences in pictures. So for a roller connection, you see there is only one reaction force. Okay, that goes parallel with the beam, right? With the support. So you see Fy, one reaction force. Now with a pin connection, we have two, horizontal and vertical. Here we have a simple beam, which is supported at both ends, a continuous, where we have multiple columns or piers perhaps, and then we have a cantilever, which is supported at one end only. It's affixed at one end. So here we have moments at each end for fixed, and we have overhang. Okay, so here's a simple beam where we have an applied load a certain distance away, and you see that we have a pin connection on the left and a roller connection on the right. So what that tells us right away is that at the pin connection, we're going to have both a horizontal and vertical reaction. However, when we see that there is no such horizontal load, then we're going to ignore that horizontal reaction force, which would be F of X. All right, as we looked at when we did POE, we went through this, right, for solving trusses, right? Some of the forces in the Y must equal zero, some of the forces in the X, and some of the moments about a simple point, or a single point, I should say, must equal zero. These are the equilibrium equations. Okay, so we're going to go through. Remember, with moment, it is force times perpendicular distance. Moment is equal to force times perpendicular distance. All right, here we have a beam. Now, some of you have not included this in your notes. I will go back and check. I did tell you to do that. I will take off points if this has not been done. So here we have a beam with a pin connection at A and a roller connection at B. The beam is 20 foot long. There is a concentrated load of 4,000 pounds P, 6 feet away from A. There is also a distributed load of 600 pounds per foot that goes across the entire 20-foot span. Now, we're going to do a free body diagram. And here we show our arrows for force Y and force A and force B. We have XA and FYA and FYB. Now, FXA, again, is going to be equal to 0. So at this point in time, I will do a quick sum of the forces in the X direction to show that there is no other force than FXA. Therefore, FXA is going to be equal to 0. Okay, so here I show it there, FXA equals 0. Now, we're going to go into our sum of the forces in the Y direction because we have plenty of forces in the Y direction. So we have force YA plus force YB minus, right? We have a downward force of 4,000 pounds minus a distributed load, which is going to be our equivalent concentrated load of 650 pounds per foot times 20 feet. We cancel out the feet, and that comes out to 13,000 pounds. And we have our 4,000 plus 13,000 comes out to 17,000 pounds. Okay, that's an equivalent concentrated load. And when we talk about the equivalent concentrated load, we look at it midpoint of the beam. All right, so let's go through and see what we have here. Okay, so we have our moments. We weren't able, going back here, we still have two unknown variables, FA and FB. We cannot, force A and force B, we cannot assume what those are at this point in time. So we're going to go to our next equilibrium formula, which is moments. And some of the moments, we're going to take some of the moments about point A. So looking around at point A, we have FYB times 20 feet minus the 4,000 pounds times 6 feet, right? That's that concentrated load, minus the equivalent concentrated load of 13,000 pounds times 10 feet. Okay, so remember, we have to include force and distance. We're talking about moment now. All right, so that gives us 20, and I am ignoring FYA. I don't know why that's in there. We are taking the moment about that point. So that is going to be 0. We're not looking at that. We're trying to solve for FYB right now. So FYB times 20 feet minus 24,000 foot-pounds minus 130,000 foot-pounds equals 154,000 foot-pounds. To solve for FYB, we divide by 20 and we get 7,700 pounds. All right, now we can jump back to our some of the forces in the Y direction, and now we can find force YA by doing some simple math. All right, and you can also make that connection that we just solved a system of two linear equations for this beam analysis problem where we came up with FYA of 9,300 and FYB of 7,700. We are far from being done here. Okay, this is where the rubber meets the road. Things are going to get a little dicey here, so buckle up and pay attention. All right, here we have our shear diagram. All right, now this looks pretty encompassing. Okay, so what we have shown here is our shear is a point along the beam is equal to the reactions, right? The upward reactions minus the applied loads downward to the left of that point. All right, so we see that our shear diagram, we start off at 9,300 pounds to reflect force YA. It slopes down, okay, to that 6-foot point. Why does it slope down? Because we're looking at 650 pounds per foot. Remember, that is a distributed continuous load. Now, it stops at that 6-foot point. Why? It goes straight down because we have 4,000 pounds coming down there. Okay, so you can see that that sloped area would be equivalent to 650 pounds per foot times 6 feet, which is equal to 3,900 pounds. That would be the equivalent load there at that point. Okay, then we have our 4,000 pounds coming straight down. If we take those two numbers, okay, we take those two numbers and we subtract them from the 9,300, we're going to come up with 1,400, and that's what's left right there. Okay, that's what's left right there. Now you see that we have that triangular area X. Okay, where we have that 6-foot point, that's where the kink in our diagram is going to be. In our moment diagram, there's going to be a kink. That kink is right there because we have a continuous load and a concentrated load that meets right at the 6-foot point. Now, it crosses the shear line X feet away from that 6 foot. We need to know what that X represents. So we're going to figure that out right now. Okay, there you see the X distance. In order to find that, we're going to take 1,400, okay, 1,400, which is our, which is that point, our load, divided by 650 pound per foot, and we come up with 2.15 feet. Okay, now, why did we just do that? All right, well, we have our 1,400 pounds. That would be that load area, and then we divide it by 650 pounds per foot because that's the continuous load, which gives us that distance. Okay, now we have our moment, and we need to determine what the maximum moment is. You see that there's a kink before we get to that max moment. There's a point 6 feet away that shows where that kink in the curve is. Okay, and we discussed that kink. That's where we have our continuous load meeting our concentrated load. All right, here we're going to solve for the maximum moment, and we have 4,000 times 2.15. And you see where we're taking it at? We're taking it at point P, which is going to be 8.15 feet away. Okay, that's at the shear. We're taking it at the shear point. And we go through our math, and we come up with a maximum moment of 45,608. okay? So what did we just do here? We did 4,000 pounds times 2.15. Okay, that makes sense. We're 2.15 away from point P, plus 650 pounds per foot times 8.15 times 8.15 divided by 2. Why are we doing that? Remember, we have to find the equivalent concentrated load of that distributed load. So we have to find it in the center. So it'd be 8.15 divided by 2. Minus, right? Minus, because you have that reaction force, 9,300 times 8.5. And that gives us our maximum moment of 45,608 foot-pounds. Okay, there's another way to solve it, which I prefer. It's much nicer to look at. It doesn't matter. All right, so we're looking at areas here. We have area A, which is a triangle, area B, which is a rectangle, and area C, which is another triangle. And we come out with, for area A would be 6 foot, right? That horizontal distance times 3,900 divided by 2. Remember, it's a triangle, plus area B, which is 6 foot, times 5,400. Okay, that's that 4,000 and 1,400 pounds added together, plus area C, another triangle, 1/2, 2.15 foot, times 1,400 pounds, equals, same thing, 45,605 foot-pounds. All right, here's a example that you can run through, which I expect you to do also in your notes, and do it exactly the same way. Although this one has just a distributed load, does not have a concentrated load, which when you look at it, you see that that shear line crosses right down the center of that beam. Why? Because there's no concentrated load to add that kink. So you're going to have a nice uniform load. You see that the reaction forces are both 9,810 pounds. Okay, and then our maximum moment there is 44,145. Our maximum shear is 9,810 pounds. All right, so run through this, and then I'm going to show you how to use MD solids to calculate it. But any questions, please ask me. You're going to need to run through this in order to successfully complete the assignment that goes along with this. All right, once again, this is Mr. DiLiegro, Truman High School Engineering. Thank you.